Good morning, everybody. I hope everybody's doing well. I hope you had a great spring break and, had a good Easter, all that fun stuff. So, I hope you relaxed a little bit. Also, did a little math every now and again. I know that I did. Yeah, like I said, I hope all things are well. We're right smack dab at the beginning still of chapter 11, just as a reminder, because it's been a week, a little over, right? So let's go ahead and remind ourselves of what we've been going through. Specifically, the two sections prior to this were sequences and series. So section 11.1 was all about sequences and how to determine whether a sequence is convergent or divergent. We define those terms as well. We also talked a little bit about bounded monotonic sequences. Any bounded monotonic sequence converges. That's a semi-important theorem. Also, if the limit as n goes to infinity of the absolute value, I should probably write that down. Limit as n goes to infinity of the absolute value of a sequence, if that tends to zero, that implies that the limit of the sequence itself tends to zero. Now, that's just sequences, all that we dealt with in 11.1. In 11.2, we reopen the door to series, adding up terms of sequences, this type of stuff right here. And one very special type of series, there's actually two very special types of series that you learn in pre-calculus. One is called an arithmetic series, and one is a geometric series. We don't deal with arithmetic series in calculus because they all diverge. But geometric series, like this right here, these will converge under special circumstances. And we learned that in that section that this will converge if the absolute value of that common ratio is less than 1 in magnitude, or I should say the common ratio is less than 1 in magnitude, or in other words, the absolute value of the common ratio is less than 1. And what it converges to is A over 1 minus R. Just to remind you of something you may or may not recall. Actually, it's not actually that big. I was going to go into it, but it's not that big of a deal for us. I was going to do the finite summation, but we don't need that at all. So there's no need to include that in this conversation here. So these are the infinite sums. We would love it if all of our series were like this, geometric. And in fact, that's something we're going to be really trying to force our series to be in the long run, is geometric series. However, it's just not the case that every series you're handed is going to be geometric. So we have to figure out a way to determine whether or not a given series converges or diverges if it's not geometric. And that's where we started into 11.3 is what do we do if we're handed a series that's not geometric? So we cannot determine immediately whether it converges or diverges. And somebody asks us, does this converge or does this diverge? Often they'll not bother asking if it converges, determine what it converges to, because that's almost impossible to find out. So we start now into, or we continue actually into this chapter with our conversation on the integral test we talked about last time, which is basically that there are three conditions that allows us to compare a series to the improper integral of a related function. So let's go ahead and I should also mention this. When we dealt with the series in section 11.2, we were introduced to the divergence test, which tells us that if the sequence itself that the series is based upon, if the sequence, this sequence right here, so the sequence terms, if that tends to something non-zero as n goes to infinity, then we can immediately say that the series, if you keep adding those terms forever and ever, that will diverge. That's the divergence test. So that's just a little heads up there. That's a really powerful test, very, very popular and very fast actually to start with any type of series problems. And now after we did that, let me just see, we we talked about this special type of series. Now, the harmonic series, a lot of people tend to say, oh, this series is somebody hands you a series, and a lot of people say, oh, it's harmonic. Let me just give you a little bit of a warning here. I have to remember what pen I'm using. Oh, good. I'm using the right pen. So a little bit of a warning is that if I hand you something like 1 over 3n plus 1, let's just say it goes from 1 to infinity, you cannot say that's harmonic. It is actually not harmonic. It's related to a harmonic series, but it is actually not harmonic. You have to determine whether this converges or diverges using something else. So I just want to note here that this is not a harmonic series. Or I shouldn't even say a, I should say the. It is not the harmonic series. And so you cannot say this diverges because it's the harmonic series. It's not. So for right now, all we can do is kind of beg to use the integral test, basically to trade this out for an integral. So please do not, when you do your justifications in the homeworks and stuff like that, please do not say that this is harmonic, because it's definitely not. Okay, that's just a heads up. I know that when I was a student, I just wanted to say, well, that's basically like 1 over n, and it is. Trust me, it is basically like 1 over n. So I don't blame you for wanting to say that. However, it's not 1 over n. So we cannot just say it's harmonic, so therefore it diverges. We have to use a little extra rigor for right now. There's something we're going to learn in the next section that will allow us to sort of relate it back to a harmonic series. Anyhow, so we learned the harmonic series, and we learned that diverges actually by just looking at the area underneath. I don't know if I did it on this one, but I might have done it on this guy right here. So we proved that the harmonic series diverges because the harmonic series is a sum of the area underneath those red rectangles, and the area underneath those red rectangles is greater than the area underneath that green curve, which is, I don't have it written here, but that green curve is y equals 1 over x. And we know from chapter 7 that the improper integral from 1 to infinity of 1 over x dx, that diverges by the power test for integrals, right? The power on that x downstairs is less than or equal to 1. So the area underneath that curve diverges. And because that area underneath that curve is less than the area of those boxes, the area underneath those boxes also diverges. And that was our proof that the harmonic series itself is divergent. Very powerful statement there. And then we moved forward and we introduced ourselves to the integral test. And here's the 3 conditions for the integral test. Suppose that you're given a function. It must be continuous, it must be positive, and it must be decreasing. And the first 2 are generally pretty quick and easy to state. Most of the functions we deal with are continuous. And then the positivity is actually a requirement for a lot of the series convergence and divergence tests. So from 11.3 to 11.4, you're only dealing with positive valued series. So anyway, that's just a heads up. So we need to state that the sequence the series is based upon is continuous and positive, or the function, I should say, that is related to the sequence is continuous, positive. And then you use a derivative to showcase that function's decreasing. If you have a function that's related to your series that satisfies those 3 conditions, then you can determine the convergence or divergence of your series based upon the convergence or divergence of the improper integral of that function, f of x. And notice I started it not at 1, but I started at just some number k here. And the reason why is because those 3 conditions, that your function be continuous, positive, and decreasing, they actually don't always have to hold. They just have to hold from some value k onward. So if you have a function that's not continuous, positive, decreasing for the first 100 values of n, that's fine. As long as for the 101st value onward, those 3 conditions are satisfied, then you can go ahead and use the integral test. And the integral test is very nice because ties us back to all of our integration techniques from chapter 7. Very, very nice to follow chapter 7 with chapter 11. And then we did, let's see, I think we did an example or 2 or 3. So yeah. So we started with this guy right here. We showed that I walked through and just said, let's go ahead and make a list. Is it geometric? Can we do the divergence test? If not, then we move on to the integral test. Okay. And then we did the integral test there. We found the related function to be basically the sequence itself with x's. And then stated it's continuous and positive, and proved it was decreasing using the derivative. And therefore, once you did all that, you're allowed to actually evaluate that using the integral test. And we noted here, by the way, when we did our u substitution at this point, we got down to this. Don't bother continuing and evaluating. We actually have a theorem for improper integrals that if the power is greater than 1 on the 1 over u to a power, if that power is greater than 1, we know it converges by the power test for integrals, improper integrals. So yeah, there's no need to actually evaluate it, because remember, the value of the convergent improper integral does not, or is not equal to the value of the convergent series. Just the fact that it converges, the improper integral converges, that tells us the series will converge, but they likely will not converge to the same value. And just in a second, somebody just asked a question just to clarify, anything after k, not at k. Yeah. So this is a question concerning when I had said earlier that as long as those 3 conditions hold for some number onward, right? So as long as you find, let's say that that your function's decreasing, continuous, and positive from x equals 10 onward, then do your improper integral from 10 onward. Okay. That's all you really need to worry about. Just find the point where it starts that decreasing and positivity and continuity. And then I think we did another one. Yep, we did. Same idea. Today we'll start up with this guy right here. All right. So let me go ahead, and I have 2 sets of notes working in the background. So I just want to get my other set of notes going. This is P series test. Yeah. So this is actually something that is very much related to what we learned previously. And in fact, did I already say it and just move on? Let me just see. No, I didn't. I guess I used that as a good stopping point. So this P series test is the same thing as the power series or the power test for improper integrals. Remember, for an improper integral, let's see. Actually, we'll just prove it. All right. So the theorem, the P series test says the following: if k is greater than 0, in other words, our starting point here, k is greater than 0. And the reason why you want it to be greater than 0 is because, well, n is equal to k, and you don't want to divide by 0. That pretty much makes sense, right? So if k is greater than 0, then the series n equals k to infinity of 1 over n to the p converges if p is greater than 1 and diverges otherwise. So that is the same statement as the power test for improper integrals. Here we call it the P series test. There we would probably call it the P integral test. So, but here P series test is what we're going to call it. And the proof is very simple. First, we go ahead and let f of x equal 1 over x to the p. It's pretty obvious that f is continuous on k to infinity because k is greater than 0. The only time f is not continuous is when k is equal to 0, so we don't have to worry about that. And f is positive also on k to infinity. So the first 2 conditions, I'm just actually proving this using the integral test, honestly. So the first 2 conditions of the integral test are satisfied. I have continuity and positivity. Also, f prime of x is going to be, let's see, that's x to the negative p. So it's going to be negative p, x to the negative p plus 1. Oops, p minus 1. was going to put a +1 in parentheses, but I'll do it like this. So basically drop the power down and reduce the power by 1. And if you rewrite that, that's just a negative p over x to the p plus 1. And that is less than 0, right? Because p is a power is in, well, okay, technically it's not less than 0 if p is negative. But we're going to assume that p is not negative here, just for the time being. So as long as p is positive, yeah, that's a negative number. And so we have that our function is decreasing, which means that we can apply the integral test. I'm going to assume, by the way, p is greater than or equal to 0. It's just because if it's not, then we have that derivative is positive, and that leads to a different conversation. So we could talk about that in a moment if you want to, but it's not that big of a deal. In fact, I should probably assume that p is actually strictly greater than 0. Just because if it's equal to 0, then you have 1 over x to the 0th, which is 1, or yeah, which is 1. And the derivative of that would always be 0. So anyhow, we now can use the integral test. So implies integral test can be used to determine the convergence or divergence of this series. Well, this is going to be super nice, because if you use the integral test, now you're looking at the integral from k to infinity of 1 over x to the p and dx. And this converges only if the power is strictly greater than 1. Boom, we're done. So that tells us that our series will only converge if the power p is greater than 1. Now, I did kind of hand wave a little bit there because I'm assuming that the power p is greater than 0. Think about it for a moment. If the power p were less than 0, then this would be a negative exponent, which means you're actually looking at a summation of n to a positive exponent that I'll call m for right now. So think about it. If it's a negative exponent, you rip the negative off and it would move the n upstairs. And now you are actually summing up a bunch of large numbers to a positive power. Those will only get larger and larger and larger. So this would diverge. That's a little hand wavy at the end there, but I hope you understand that if I move that n into the numerator because exponent's negative, that it just keeps growing as you add terms. That's why. All right. So that's a pretty solid, decent proof of that theorem, and it uses the integral test, which is awesome. And so let's go ahead and see what the impact of that statement is. It's actually not super impactful, to be honest with you. You don't get down to this form very often. You get down there somewhat. You commonly do get close to it, but not exactly. Let's go ahead and see what we're going to do here. Determine if the following series is convergent or divergent. Now, knee-jerk reaction, I could totally tell you right now it's convergent. I could tell you that because it's basically n to the third power. And by that theorem, the p-series test, we know that that's going to converge. But that's not a proof that this converges. It's just kind of like hand waving a bit in a way. And because we're sort of saying like, hey, guess what? This is kind of like, right? So I'm just going to say it should make sense that this converges because it's almost, it's not exactly, the summation 1 over n cubed. What we want to do is transform this and build a skill that's going to be incredibly powerful and necessary in differential equations. So we're going to transform this slightly. And the way we're going to do this, the goal, let me write that down. We have a goal here. Our goal is to rewrite this as a summation 1 over k cubed, where k is some number, who knows, right? But we want to rewrite it like that. So let's see how we're going to do that. The first thing I'm going to note here is that notice that both of these terms are divisible by 2. So I'm going to start by factoring out a 2. That's kind of important here. So let me just showcase this very slowly. This is going to be a summation n equals 1 to infinity of 1 over 2 cubed times n plus 2 cubed. I hope everybody's with me so far. That's not a huge jump in mathematics. I just factored out 2, and because it's being cubed, it becomes a 2 cubed. So this is the same thing as 1/8 summation n equals 1 to infinity of 1 over the quantity n plus 2 and quantity cubed. Now that's very, very close to 1 over n cubed, but it's still not 1 over n cubed. Let me just make that note. This is not 1 over n cubed. So we cannot use the p-series test yet. So now notice how exact we're being here. We're doing a lot of arithmetic, and well, a little bit of arithmetic, and we're about to do a little bit of algebra just to massage this problem a little bit so that it turns into this. It's kind of magical. It's something you're going to have to do in differential equations, so I might as well get used to it right now. So how do you do that? Well, the easiest way is to re-index. So I'm going to write this in here. Let's re-index. And that is such an important tactic that I really want you to pay close attention to how this is done. Look at where I want to be. I want it to be a 1 over n cubed, or 1 over, maybe I should say, a picture cubed. And it basically is a 1 over a picture cubed right now, but I need that picture to be the same thing as this variable right here. So notice it's an n plus 2, not an n. So what I'm going to do is go ahead and say, let's trade out that n plus 2 for a different letter. We're going to let k equal n plus 2. Well, if we did that, we'd have 1/8 times the summation. I'm not going to write down the lower limit there. And it'd be 1 over k cubed. Super nice. Now let's figure out what k is if n is 1. If n equals 1, because that's where we're starting, then k is equal to 3. Just 1 plus 2. So I'm going to start at 3 here and go to infinity. And you can double check, by the way. If k is 3, I have 1 over 3 cubed. If k is 4, I have 1 over 4 cubed. Go up to here. If n is equal to 1, I have 1 over 3 cubed. If n is equal to 2, I have 1 over 4 cubed. It's the same exact summation, but now I have it written in such a way that I can actually say, yep, by the p-series test, this will converge. So, and this converges by p-series test. And you do want to, name the tests that you're using. We're going to have quite a few by the time we finish out this this chapter. So you'll want to be able to state what test you used. Okay, so let me zoom out a little bit. Notice that was a very short problem as far as work goes, but I spent a little bit of time kind of slowly going through it. The main reason is because a lot of students, and myself included when I was a student, love to say, that's basically 1 over n cubed, but that's not a proof. So you really want to take your time with this, be somewhat rigorous. Okay. All right. So that's that guy right there. If there are any questions, please go ahead and jump in and ask. I'm going to have a little bit of chai. Let me mute myself while I drink. All right. So I'll hop forward here. And again, if you do have questions, feel free to ask them here, because our only goal today is finish out this section. Although if we finish early, then I'll probably step into the next section. If you're curious, we do not have a quiz today. The reason why is because twofold really, because you just got back from a long break and your brain needs a little bit of time to, go back in gear. That me too, by the way. Um, and so we'll have the section 11.1 quiz on Wednesday. The second reason is because I just have to take my father-in-law to get his second COVID shot today. So right after office hours. So that's another reason why. Oh, and I got my first COVID shot. I'm very excited about that because I had to wait so long to get it. So and hopefully the government can't track me now because they implanted something in my body, right? All right, anyhow, I don't know what that means. All right, so determine if the following series is convergent or divergent. So let's go ahead and approach this as if you're working on an exam. Notice I don't tell you, hey, use this test to determine whether this is convergent or divergent. I don't want to do that to you. I want you to get used to thinking about all the possible tests you can use. So let's go ahead and quickly go through and list out a few possibilities. The first one I always kind of dive into is the divergence test. Let me actually write that cleanly. So the first one I think of is the divergence test. But if you think about the divergence test here, as n goes to infinity, that I'll just put it in here just so you can see it. Limit as n goes to infinity of the sequence is not zero. So divergence test is inconclusive. In other words, it's not going to be very useful. So then I think about, well, maybe it's geometric. This is not geometric, but I'm going to write that down anyway. I'll just say geometric with a question mark. And the answer here is no, because it's not equal to the summation of something to the nth power. Okay, that's all I need to know. It's just not a summation of something to the nth power. If it were the summation of something to the nth power, then geometric all the way, I would just dive right into it. But it's not. And then you think about other tests. Well, the only other test we have seen, and it's not really a test, but the only other tactic we've had is if it's telescoping. And I'm going to tell you right now, this is not telescoping, but I'll put it in here as a question to myself, although I rarely actually check to see if it's telescoping. But the reason why I know it's not is because telescoping sequences require you to subtract things off. Why is it not zero? Oh, I'm sorry. It is zero. Thank you. Thank you very much. Oh, sorry about that. I'm like, why is it not zero? What are you talking about? Yeah, it is zero. Thank you for catching me. Thank you for still being awake. Yeah, the limit. Sorry. Hong was just asking, why is it not zero? The limit of the sequence. The limit of the sequence is zero. And so we cannot use divergence test because when your limit of your sequence is zero, it doesn't tell us whether it's going to diverge or converge. We just don't know. If it's non-zero, that's when you know it's going to be divergent immediately. Sorry about that. Thank you very much, Hong. I really appreciate that. Sorry about that. Anyway, going back to telescoping, I know it's going to be telescoping or possibly telescoping when I can see that one term is going to be positive and the next term will be negative. But in this case, if you just look at this, it's going to be positive, 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 right? If you start adding up terms, it's a bunch of addition. No subtractions are in there. Nothing cancels out. So it's not going to be telescoping. So then the only other choice I have right now, integral test. So let's go ahead and just write that out, integral test. And actually prior to jumping into the integral test, I tend to want to make sure, is it a P series? In other words, is it harmonic or whatever? Actually, harmonic and P series are very close to each other. So I'm just going to put in here P series. And the answer to that is it's not. Even though I would agree with you 100% that is 1 over n squared. I totally get it. It's not, though. Right? It's very much like it, but it's not 1 over. But I totally know this is going to converge because it's like it. But you can't just say it converges by the P series test. Again, please do not say this converges because it's a P series test. It's not a P series. Okay. So you could, I suppose you can complete the square. Nope, you can't complete the square there. So we're going to have to use the integral test. So let's go ahead and do that. We're going to let f of x equal 1 over x squared plus 4. We know f is positive and continuous. In fact, it's always positive. It's always continuous. It's never, you never have division by 0 there. And no matter what you plug in for x, it's always positive. So first two conditions, easy breezy. And then f prime is equal to, and then we'll just do the quotient rule here. Derivative of the numerator is 0 times who cares, minus the numerator times the derivative of the denominator over the denominator squared. And that is definitely a negative number because it's negative 2x over x squared plus 4 squared. That's less than 0 for positive values of x. And we are only concerned with positive values of our inputs here. So because I have positivity and continuity, and I know that my function is decreasing, I can now use the integral test. The integral test requires you to say all this stuff. I know that I harp on this, I'm saying it a lot, but it's really beneficial for you to hear it every single time that you have to use those three conditions. So let's go ahead and just dive right into the integral test. The integral from 1 to infinity, since that's what our summation was, we might as well just go ahead and do that, of 1 over beautiful x squared plus 4 dx. Now, a lot of you may memorize how this will result. I don't. Actually, let's see if we can do a comparison test. Remember, there's a lot of things you can do to showcase an improper integral converges or diverges. You can just either evaluate it, or you can use a comparison, right? You could just say, well, note x squared plus 4 is greater than x squared, and therefore 1 over x squared plus 4 is less than 1 over x squared. And by the way, those are both positive. This is harken back to chapter or section 7.8 when we were introduced to improper integrals, and then we spent some time evaluating them. And at some point near to the end of it, we said, well, what if we could compare them? And so note the integral of 1 over x squared dx from 1 to infinity converges by power integral test, not power series, but power integral test, right? Because its power is greater than 1. And thus, the integral from 1 to infinity of 1 over x squared plus 4, because 1 over x squared plus 4 is below 1 over x squared, by our statement right here, the area underneath 1 over x squared plus 4 must be less than the area underneath 1 over x squared. Well, the area underneath 1 over x squared from 1 to infinity is finite. So the area underneath 1 over x squared plus 4 must also be finite. So that's converges by integral comparison test. I should probably write that in English here rather than shorthanding that. Integral comparison test. It's kind of nice to do. And now that we know that our improper integral from 1 to infinity of 1 over x squared plus 4 converges, we know therefore that our series converges. And the reason why this series converges, by the way, is by the integral test. That's the primary reason why we determined that this series converges. We compared it to an integral. So I've coded a lot of problems in this homework. In fact, maybe I should just share my screen so that you guys can see that. I want you to be able to see the assignment. Let me bring it up real quickly. Teacher preview. And let me go ahead. Could we go straight into the comparison test? No, you can't go straight to the comparison test because there's no such thing right now for us as a comparison test for series. We only have comparison tests for integrals. To be honest with you, in the next section, we'll have a comparison test for series, but it's for right now, we only have it for integrals. Okay. It's just an important little note. Give me a moment. I just found that one of my problems is already broken. So let me fix it really quickly. Questions, action, edit. And quick save preview. What's going on? I'll have to find it in there. I'll fix that right after lecture. There's no need for me to fix it right now, but I'll share my screen. Yeah, I'll go ahead and do it. It takes me a few moments to hop back and forth, but I'll go ahead and do it right here. So here is the assignment. I'm bringing it up right now. You'll see that on my end, there'll be something that's broken in a moment here, but I'll just showcase this anyhow. So some of these problems I have coded. It's problem 4. You can see I have a problem with problem 4. I'll fix that in a moment. But on the questions that I've coded, they look like this. There's 3 questions. And here's a series. First, determine whether it converges or diverges, and you'll do some test to do that. The primary test that you're going to use, let's pretend that you use the integral test. So under this, you'd say I used the integral test. Or let's say that you found it diverges by the divergence test, then you'd select that. Or if it's geometric and you found it converges because geometric or diverges because of geometric, then select that. The only time you're ever going to select harmonic series is if it's just literally the harmonic series. Therefore, you're never really going to select that one. And then P series, the only time you'll select that is if it's a direct P series, like let's say a 1 over n to the 8th or something like that. So you select that. So in this case, I'm going to tell you that I would probably use an integral test here. And then within using the integral test, I would probably use, I suppose I could do basic integration, right? Or a comparison test. So it'll allow both of those. Basically, these are coded to have multiple possibilities for where you went after you did your first major test. What I want you to do is when you do the homework, if you find that you did a direction, and let's say you did the integral test first, but you found it converges, when you did your integral test, you did something else and it marked you wrong, email me or send this to me because I want to make sure this gets fixed very quickly, so that I can fix the question code, or it could respond back and say, oh, no, when you do the integral test, you can't follow that up with using whatever. So in the problem that we worked on here, let me get back to my screen. Share screen. Yes. Go to share. Bring this down. Zoom that out. Okay, so in the problem this problem right here, we found it's convergent, and we found it's convergent by the integral test. That's the primary reason why it converges. But the secondary reason is when we actually performed the integral test, we found that it was convergent. We could select either by the P integral test, right? The power test for improper integrals, or the integral comparison test. Either of those are acceptable. So just when it says that, what's your secondary reason, basically why, when we're using the integral test, why could you tell me that the integral converged? It's one of those two. So just be aware that you are my beta testers for that code. So sorry about that. Okay. And then I'll fix that problem number 4 when I get around to it right after lecture. All right. So let's go ahead and now finish out this material with a very important topic that when we did, what was it? Numerical integration techniques. When we did numerical integration techniques like the trapezoidal rule or Simpson's rule, or midpoint method or whatever it is, we got to these formulas where it was like, okay, but the error using, I think we called it E, the error using a trapezoidal method is less than or equal to K times B minus A to the power whatever over some numbers, right? And we then had to worry about what that K was. It was a big nightmare. And then I had mentioned, like, okay, to be honest with you, I don't expect you to really worry about that. And you noticed it wasn't on your exam. And the reason why is because that's more for a numerical integration course, a course that's really focused on learning numerical integration techniques. However, with series and summations, it is important for you to be able to use error estimates. So we're going to have a little bigger conversation here. These are going to be required knowledge pieces. So let's start with a very clean, nice definition of a remainder of any partial sum. So you have some summation. Let's just say it's a summation n equals 1 to infinity of a sub n. Okay, so you have some sequence you're adding up forever and ever and ever. Well, we are going to define the remainder, the nth remainder. We're going to define that. That's what the triple equality means. It means defined to be. So we're going to define that to be the actual sum. Let me make that a little bit bigger. The true sum over the nth, or minus, sorry, the nth partial sum. So that should make sense that the stuff we didn't add up, that's what we're calling the remainder, is equal to the true summation, the infinite sum, minus, well, the sum of the first n terms. In other words, if you did that, you'd have, if you subtract off the first n terms, you'd lose a1 plus a2 plus a3 plus a4 all the way to an. You'd lose all those. And you'd be left with a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3, and so on and so forth. This is also known as the tail of the series, because you basically have lopped off the big chunk, the beginning, the first 20,000 terms, and you're left with actually a massive list at the end, the 20,001st to infinity term that you're adding up there. That's the tail of the series, the stuff that you did not actually add up. And that tail of the series is defined to be the remainder or error. So that's, in fact, what I'm going to call it. So we're going to call that the error made when we use S sub n to approximate the exact sum S of a series. Okay. So if somebody says, hey, I need to know, for example, what is the error if we only add the first, let's just say, 10 terms of the series n equals 1 to infinity a sub n, question mark. Well, that error, which I'll call, we call R, honestly. Oh, that's not going to erase. So R sub 10, that's the error, is going to equal a 11 plus a 12 plus a 13, and so on and so forth down the line. It's just basically all the stuff that we forgot to add. That's our error. So we did a pretty good job, I suppose, but there's a terrible error there. Now, obviously, if you want to find out what the error is, that's an infinite sum. I don't want to add up a bunch of stuff forever and ever and ever. I could tell you if that summation converges, but I cannot tell you what it converges to. All right. So that's where we get into how can we approximate the error. Sorry. So let me point an arrow at this and say, this is still an infinite sum. I'll put in here, we can determine convergence, maybe, but not its value. Normally. Okay. If it's geometric, you can actually determine its value. But if it's not geometric, you just can't determine its value. So what are you going to do? Well, we need a way to approximate this error. And that gives us the next theorem, which is page 11 of 13. We're very close to the end of this section. Now, don't be too intimidated by this because it comes down to only one little inequality, generally speaking. And for me, it actually only comes down to one inequality, this whole entire statement. But let's just go ahead and read through this first. The remainder estimate for the integral test. Now, let me also tell you, this is only for the integral test. This is not for any other test. It is only for the integral test. So if you can use the integral test, this is how you can estimate the error if you had only added up the first 5 terms. And I also want to mention, if you hop back to our definition here of the remainder of a partial sum, I hated this when I was a student. I was like, hold on, you're telling me that if I am able to compute the error, to be able to compute the error itself, I need to know what the actual sum is? Well, if I know what the sum is, then why am I approximating it? If I know what it sums to, then why am I just adding the first 10 terms? I already know what it sums up to, right? So this initial definition to me was always, I always hated it. I thought this is a terrible definition because, again, to the nth remainders or the error is defined in terms of knowing the true sum. However, in the theorem here, we're saying, well, we don't know the true sum, so we're going to approximate this error here by bounding it. All right, so suppose that we can create a function that's the same thing as our sequence, which is obviously incredibly easy. Just trade out x's for n's, okay? And suppose that function is continuous, positive, and decreasing eventually. That's what this means for x greater than or equal to some value of n. And suppose that also our summation, our infinite series, is actually convergent. If it's not convergent, there's no point in us saying, hey, how bad is our estimation? The reality is that if you add up the first 10 terms for a divergent series, well, because it diverges, it'll either go up to infinity, negative infinity, or just won't exist. So there's no such thing as an error in that situation. You can only have errors when you have a target of like, if I know it converges, if it converged, this series converges to 5, my target is 5. I throw the dart at the board and it doesn't hit 5. It's slightly off. That slightly off is my error. Okay. So let's talk about this. If all 3 of those conditions are met, in other words, we were able to use the integral comparison test and our integral actually converges, then the error is bounded above and below by these 2 integrals. It's bounded below by the integral from n+1 to infinity of our function. It's bounded above by the integral of n to infinity of our function. Let's see why that's true very simply before I go into the rest of this. The rest of this, by the way, is just saying R sub n is the same thing as S minus S sub n. So that's all I did from there to there. R sub n is just equal to the true sum minus the sum of the first n terms. And then if you add the sum of the first n terms to both sides, you get this. And this is kind of just saying, well, I know the true sum is somewhere between these 2 values. Now, to be honest with you, of all of these, inequalities and things, this is the one you're going to use. The stuff that I'm highlighting right here. Just that. You just want to know what's the upper bound. How bad can our error get? That's generally the one you're going to use, okay? But I still want to at least give you a visual justification as to why the very top inequality is true. Let's go ahead and just give a small visual justification. First of all, if the summation a sub n, let's call it a sub k because I want to match my notation. If the summation a sub k converges, then the limit as n goes to infinity of a sub n, as k goes to infinity of a sub k, we know that's going to be 0. If it's non-zero, in other words, if that limit doesn't tend to 0, we know it would diverge. So therefore, if the summation is convergent, we know the limit of the sequence will be 0. Why am I writing that? Well, because that just tells me that if I were to draw a horizontal x-axis here, that our function we're comparing it to has to tend to 0 as time goes on. I hope that makes sense. Now I'm going to write in here 1, 2, I'm just dicing this up, 3, 4, 5, and so on and so forth. And there are 2 ways that you can approximate the area underneath this curve. You can use right endpoints or left endpoints. If I use right endpoints, well, I'll use red for right endpoints. If I use right endpoints here, then the area that you're looking at right here is actually a sub 2 because I'm using the height at 2. That area is a sub 2. And actually, this area over here is a sub 1. Okay. But we're not going to worry about that. I'm just showing you that that would have been a sub 1 over there. All right. So let me see if I can erase this off. Come on. Erase, erase, erase. There we go. And this area right here is a sub 3. And this area right here, again, because the right endpoint is at x equals 4, the area that's a 1 by f of 4, or in other words, it's a sub 4. This is a sub 5. Well, if the area underneath f is finite, which we're assuming by this, that f is a continuous positive decreasing function, and we know that it's that our function, our series, is convergent. Therefore, our function must also be convergent. If that's the case, then since the integral from 1 to infinity of f of x dx is finite, finite, that will tell us that the summation from k equals 2 to infinity, because I'm starting at a sub 2 there, of a sub k is finite. Well, it's also less than, right? It's less than finite and less than integral from 1 to infinity of f of x dx. Okay, great. So in this case, I know that we have the following. Let's see, the summation. Actually, I'm going to do a second picture here before I do the other one. We can also do left endpoints. I'll do the same exact slicing here. 1, 2, 3, 4, and 5. I'm just getting these nice slices in here. In this case, I'm going to do left endpoints. And if you do left endpoints, which I'll do in green, you can see the area underneath the boxes is above the area of the curve. And this area is a sub 1, this area is a sub 2, this area is a sub 3, this area is a sub 4, and so on and so forth, right? So this tells me that the integral from 1 to infinity of f of x dx is below the summation from k equals 1 to infinity of a sub k, right? And now we can, that kind of provides a nice bound for what we're doing here. So let's go ahead and finish this out. Let's see, how do I want to do this? If this is finite, I'll go ahead and go about it this way. Summation 1 to infinity. Yeah. Okay, so what if we were to say, instead of going from 1 to infinity, that we go to 1 to, I think I'm gonna destroy this proof if I try this out. Where do I want to end with? I need to get to n plus 1. Oh, I know what I could do. I could say that this is this first one right here. I could say that a sub 2 plus a sub 3 plus a sub, yeah, that's a good way to do it, plus dot 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 all the way to a sub n. So I ended my picture at a sub 5, but the reality is we can go all the way to a sub n. That's going to be less than or equal to the integral from 1 to n of f of x dx. Again, that just matches up with our picture right there. Okay. Let's see. And if that converges, how am I going to get a sub 1 in there is my concern. Because if I want to shift this over 1, that's going to be a problem. So I'm sort of concerned with that. I'll have to think about this one. I was going to just barrel right through it, but something tells me that something I'm just missing a little bit in here. I want the n to infinity. You'll have to forgive me on this one. For some reason, it's not jumping out at me as to how to make that work. It does work. So I'm just letting you know that this statement right here is true. Just for some reason, it's just not jumping out at me as to why. I mean, not as to why, but as to how to prove it fully. So what I'll do is, if I can, but when I get around to actually doing it, I'll make a slide video just proving this. I apologize. I did not actually prep for the proof of it. So been busy. So I will go ahead and make that a little bit later. I apologize for that. But we can at least use it. We'll just use it for now, because that's what you're going to have to do in the homework. So I want to make sure that we can. So let's go ahead and just take a look at a simple series here, and then we'll go through, and maybe this will kind of jog my brain on how I want to get that proof finished. So let's go ahead and do this guy right here. We have a series n equals 1 to infinity of 1 over n squared. First of all, we know this is convergent by the p-series test. Let me just point an arrow at that. Convergent by p-series test. And when you use a p-series test, by the way, it's a very special subcase of the integral test. So it really, you could have proven it converges by the integral test also. it converges by the integral test. And if you can use the integral test, that means that you can estimate the error if you only want to add up the first, let's say 5 or 20,000 terms or something like that. You could say, well, if I want an approximation of the value of this summation, and let's just pretend as though you can't find the exact value of the summation, but you want to add up enough terms to where you get a certain level of accuracy, the error bound that we have back here, this guy right here, will be incredibly helpful. Let's go ahead and see how that works. It's really very nice. We'll start by using technology. That's critical here. Use technology to find the sum of the first 10 terms. Now remember, S sub 10 just means I want to know what is the summation. Actually, I should probably say S sub 10. S sub 10 is the summation n equals 1 to 10 of 1 over n squared. All right, so let me show you using technology how that's done. I think I've shown you before, but it's opening up Desmos. But I wanted to show you again how that's done because you're going to use it on the homework, so you might as well see it a couple times, right? So let's go ahead and hop over to Desmos. There we are. And I think I might have mentioned this, but if you go into math tools here, if you select the scientific calculator, the summation does not work there. I've never been able to get it to work. However, it does work in the graphing calculator. So I'm just going to go to the graphing calculator and type the word SUM for sum. And then I'm going to go from 1 to 10 of 1 over n squared. That's it. So we could see the summation, I'm going to write this down on my writing tablet here, is roughly 1.5497. I'm going to write out as many digits as possible. 6773 and 117. Let me go ahead and go back and share my laptop. Going back, share, yes, right here, share. Okay. That's pretty easy. Just summing up, using technology to help us sum the first 10 terms. Nothing big. I would not have you do that by hand. That'd be just no fun, right? It would be 1 plus 1/4 plus 1/9 plus 1/16. It just, you'd have to add a bunch of fractions. No fun. So let's go ahead and improve this estimate of our true sum. By the way, that's not the true sum. It's an estimate for the true sum by using the following inequalities with n equals 10. Now, if this were on an exam, I'd probably provide you with this specific inequality. However, it is important that you do remember. So this is this one right here. This is memorizable. But this inequality right here, not so much. I would hand it to you if I need to. So in this case, I'm asking you, well, what is the true sum? Can we figure out what the true sum is between? And the answer is absolutely you can. You know what the sum of the first 10 terms is. It's 1.54976, so on and so forth, right? And same thing on the other side. Yeah. 1.549767 73117. Okay. Oops. Less than or equal to. All right. We know that we have those two, right? Those are the S sub n's. But now we can evaluate the integral of the function of the related function to the sequence from n to infinity and n plus 1 to infinity. And remember, in this case, n is actually 10. So we want to take a look at the integral from 10 to infinity of 1 over x squared dx, and the integral from 11 to infinity of 1 over x squared dx, because that's what these two integrals are here. Okay. And the integral from, it should make sense, by the way, the integral from 11 to infinity is less than the integral from 10 to infinity because it's less area. in both cases, you're just going to quickly do this. Limit as t goes to infinity, integral 10 to t, x and -2. That's supposed to be an x, but it just got kind of messy. Dx. And because we're being asked to evaluate this, that's why I'm actually doing the limit here. Negative x to -1, or in other words, -1 over x from 10 to t. And let me go ahead and erase this and get it out of my way. I'll deal with that in a moment. And this is going to be a limit as t goes to infinity of a -1 over t plus 1 over 10. Now, as t goes to infinity, that's just going to be 1/10. And likewise, we can use that as a template for the integral from 11 to infinity. That's going to be 1/11. All right. So now I can easily say that my estimate is somewhere between 1/11 plus that number or my true value of the sum is between 1/11 plus s sub 10 and 1/10 plus s sub 10. And if you want to know what those values are, this is just to improve our estimate. We can go back to Desmos really quickly because, well, we have the numbers in there. So you can go back here and you could just say, I'm going to call this, let's call this A is equal to that. Then I'll just say, well, this is the lower bound is 1/11 plus A. And the upper bound for our summation is 1/10 plus A. So I know that the true sum is between 1.64067 and stuff, right? And 1.649. So it is a pretty tight bound. In fact, I'm going to write those down now that I have those. So the true sum is somewhere between, I'll just write it as 1.6407 and 1.6498. Okay, and then I'll hop back to my screen. Now, the important thing to note here is that is a rare question. People don't actually ask like, okay, well then what's the sum between? That doesn't actually happen. What people really ask for is what's the error. So let me just go ahead and try to be as clear as possible with that. Getting everything arranged on my desk here. All right, perfect. All right. So again, in this problem, just use technology to add the first 10 terms, then used that summation of first 10 terms along with the previous theorem, the remainder estimate, to go ahead and say, well, our true sum, the true sum of the infinite series is somewhere between these two numbers. Now that's, again, typically not what people will ask. What people will ask, no, the true sum is, so it's just being asked, is the true sum, is that what we found using technology? No, the true sum, what we found using technology is an estimate. It's the sum of the first 10 terms. The true sum is the sum of the first infinite terms, right? All the terms in the series. And there's no way a computer is going to be able to do that. So, and we can't actually find the value of this, by the way. You cannot find the value of this true summation. With whatever you want to try, you can't find this value. So instead, you can estimate the value. And that's what we just done. We've said, well, if you sum up the first 10 terms, then I can estimate the value of the true sum because it is between the sum of the first 10 values plus the integral from 11 to infinity of our function and the sum of the first 10 values plus the integral from 10 to infinity of our function. So that's one tactic that people will take with this, but to be very honest with you, that's not how you're going to do this in practice. So if you go into engineering or something like that, what you're going to want to do is say, somebody's going to say, I need you to work on this. By the way, we can't have an error above 0.001. Well, if somebody tells you the bound on your error then you, from that information, you could say, well, then I'm only going to add up the first 20 terms or whatever it is. So in this case, this part C is the most important problem for all of us, actually. Part C is very, very important. Use the remainder estimate to find a value of n for which our sum will approximate the true sum to within 0.01. What does that mean? It means we want our error to be less than 0.001. Well, technically they said to within, so I'll say less than or equal to. So it doesn't really matter. It could be, like you could do strict if you want to, but when they say within, I generally consider that includes the edges. It's a habit I have to make for an assumption. So this goes back to what I say is the important inequality. I happen to know that the error is always bounded by the integral from n to infinity of f of x dx. If you have proven that the series converges using the integral test, then you could say the error, if I only add up the first n terms, will always be bounded above by the integral from n to infinity of f of x dx. Let me go ahead and write that. So this error we want the integral from n to infinity of f of x dx to be less than or equal to 0.001. We want our maximal error to be less than or equal to that 0.001. And now we can go ahead and evaluate our integral. Remember, we were integrating 1 over x squared dx. And remember that improper integral, whether we evaluated it from 10 to infinity or 11 to infinity, it became 1 over 10th or 1 over 11. So if it's from n to infinity, it's just going to be 1 over n. Just using pattern recognition here. So this is going to be 1 over n is less than or equal to 0.001, which, by the way, is 1/1000th. And now take the reciprocal of both sides. And when you take the reciprocal, you flip inequalities. And this tells us that to get that level of accuracy, we require that we add up at least the first 1,000 terms. Okay. That's not too terrible. By the way, if it annoys you that I skipped the integral, it's not that big of a deal. You can actually do the entire integral if you want to. This would imply the limit as t goes to infinity, right? You'd have to do it this way, but you could totally do that. Integral n to t x to the negative 2 dx, right? And this is equal to the limit as t goes to infinity of negative x to the negative first from n to t, which is equal to the limit as t goes to infinity of a negative 1 over t plus 1 over n. And that would be as t goes to infinity, a 1 over n. That's why that is that way. So the remainder estimate for the integral test is actually a really nice one. The only one I really think you should worry about, again, is this highlighted inequality. The error when you add up the first n terms is always bounded above by the integral from n to infinity of f of x dx. If you got that, you're good. Now, one example is not going to do it here, so let's just do one last one and call it good for this. Oh, actually, that is, I guess that is my only example there. I forgot that this ends with my how-to. So I thought that we had an extra example, but I guess we didn't. All right. So as I mentioned at the end of last class, every single one of these sections from this point forward, we end with a summary of everything we've learned so far. So somebody gives you a series, somebody being me, during an exam, right? Or actually in engineering, you deal with series all the time. And they ask you whether that series converges or diverges. Well, if you think it diverges, then the only possible tests that are going to work for you is the divergence test, which is really probably the best one to try first. If the limit of the base sequence's function is non-zero, then the series diverges. If you can't use the divergence test to showcase divergence, then, well, if you have a geometric series, then you know that it's going to diverge if the common ratio is greater than or equal to 1. If you're using the integral test, well, if the function associated with the base sequence is continuous, eventually positive and decreasing, and if its improper integral to infinity is divergent, then the series diverges. So basically the integral and the series converge or diverge together. And then a very special subcase, p-series test, which you can't use that often, honestly. If the base sequence is of the form 1 over n to the p, then the series diverges if the power is less than or equal to 1. If, on the other hand, you have a convergent series, notice we have one less test because the divergence test says nothing about convergence. It only showcases divergence. So we'll always have one fewer test for convergence than we have for divergence, at least this early. And if it's geometric, you can actually figure out, first of all, that it converges if the common ratio is less than 1, but in magnitude. But you can also find out what it converges to. That's the unique situation. You know what it converges to only if you have a geometric series. If, on the other hand, you were able to use the integral test, well, then it's convergent if the associated integral is also convergent. Improper integral is convergent. And if you use p-series test, it's convergent if the power is greater than 1. That's a summary of our tests so far on whether or not a series is convergent or divergent.